that you've identified in your data via relationships with other elements. Inferential statistical analysis infers properties of a population as a whole by testing just a sample. And these two broad categories explain the two hats that a data professional wears. One, where you're responsible for finding the dots, identifying the important elements in a data set, and another, where you're responsible for connecting the dots, explaining those elements via relationships with other elements. When you're working in the real world, neither of these problems is particularly simple to solve. There are common problems that hinder analytics in both of these categories. Let's talk about finding the dots first. Today, in this day and age, data is more and more plentiful. Often, when you're seeking data to perform analysis, you might encounter a problem of plenty. However, data may not always be in the form that you want it to be. Careful handling might be needed before the data can be useful. You might find that in the real world, the data that you get to work with is often incomplete. It might have a missing values, fields, or entire records that are missing, or it might have outliers within it. Now, some of these outliers might be genuine outliers. Genuine outliers are data points that are unusual. Maybe they have too high or too low a value, but they are real data and contain information. Very often, though, outliers might just be data points that have not been measured or calibrated correctly. Based on whether outliers are genuine or errors, you might have to deal with outliers differently. When you're collecting data for analytics, these are some of the common problems that you encounter. In addition, your data might contain duplicates, or your data might just be bad, useless for the information that you're seeking. Let's say you've successfully managed to solve the finding the dots problem. That's when we'll move on to the next step, analysis or connecting the dots. Now, there are a variety of tools that you could use for this. The easiest and the most intuitive tend to be spreadsheets, which represent your data in a tabular format. Or if you're familiar with programming, you might choose to work with data using a higher level programming language such as Python or Java. Programming languages can be used to work with data beyond the prototyping phase. They tend to be more powerful and more robust. Programming languages give you the choice of in memory processing of your data or distributed processing on a cluster of machines. Or if programming is not your cup of tea, you might want to analyze data using SQL or the structured query language. SQL can be used with relational databases for small data sets or data warehouses, which hold very large data. The choice of technology that you make to process your data depends on what it is that you're trying to achieve. Let's say you're looking for very fast prototyping and an intuitive user interface, you'll choose to go with Microsoft Excel. Data analysis using Excel can be brittle, though it's not really great for production use. If you're looking for something more robust, you might choose to program in Python using pandas and other data science libraries. Python is an easy to learn programming language, that's why it's so popular. It also has a variety of amazing data science libraries that you can harness. Python gives you fast prototyping in an interactive REPL environment, where REPL stands for Read, Evaluate, Print Loop. However, when you work with Python and data science libraries, this still gives you just in memory processing of data, which isn't really great if your data set is large. If you're unfamiliar with or uninterested in coding, you can work with data using the structured query language or SQL. The Microsoft Azure platform offers you SQL databases on the cloud. This is a managed service, making it very easy for you to work on relational data. This is not yet big data, though. Relational databases still work on relatively small data sizes, and you'll have the problem of data silos, where your data may not be well integrated with other teams in your organization. If you're working on large data sets and you're looking for fast prototyping, you can use the Python programming language with a framework such as Spark. Spark is part of the Hadoop ecosystem. It gives you distributed processing on a cluster of machines. but you still need to write code. A no-code option that you can choose to work with big data is to use SQL with a data warehouse. A data warehouse integrates data from a variety of disparate sources. It can work with streaming data, and it also offers ML or machine learning integrations. We've discussed earlier that a common problem that you encounter when you work with data in the real world is missing data. Now, there's no way around this, so we have to deal with this. How? Well, there are two broad ways to deal with missing data. One is where you throw up your hands and you say, I have no idea what to do with this record which has missing fields. You go ahead and delete that record. However, deleting data with missing fields and values can cause significant problems with analysis. So, another technique that you can use to deal with missing data is imputation. In statistics, imputation is the process of replacing missing data with substituted values. Let's talk about using deletion to deal with missing data first. Deletion is also known as list-wise deletion, where you delete an entire record row if a single value or a field within that record has a missing value. The idea behind list-wise deletion is simple, and it's also simple to implement, but it can lead to bias. Simply deleting records can make the handling and analysis of the data more arduous, time consuming, and less efficient in general. But you'll often find that this is by far the most common way to deal with missing data because it's the simplest. There are several problems to using deletion to deal with missing data. The first of these is the fact that simply deleting records can reduce the sample size that we have to work with. For very large data sets, this may not be a problem. But if our data set is small to begin with, if you delete records with missing data, you may not have that much data to analyze. The second is a problem of bias. If values are not missing at random across your entire data set, if you get rid of missing data, this might introduce a significant bias in your analysis. It's quite possible that after you get rid of all records that have missing data, the data set that you have to work with is not representative of the population as a whole, and that's not good. To overcome these drawbacks introduced due to data deletion, imputation is often used to deal with missing data. This is where you'll fill in missing column values rather than deleting records with missing values. Data imputation refers to a category of techniques. It's not a single technique. Imputation methods can be very simple indeed or can be arbitrarily complex. The simplest way to fill in missing values is to simply calculate the average of your column of data and fill in all missing fields with this average. Another technique is to use interpolation. You simply consider the values around the missing data and interpolate the missing value from values that surround it. If you want to fill in missing data using complex techniques, you can even build a machine learning model used to predict missing values. And that's often done in the real world. Let's briefly discuss three techniques that you can use for imputation to fill in missing values. The first of these is hot deck imputation. You'll first sort all of the records that exist in your dataset based on a criteria of your choice. And for every field that has a missing value, you'll use the value from the previous record. So for each missing value, use the immediately prior available value. This technique is often referred to using the acronym LOCF, which stands for Last Observation Carried Forward. If you're working with time series data, using this LOCF technique is equivalent to assuming that there is no change in your recording since the last time you measured the value for this field. When you use hot deck imputation using LOCF, the last observation is carried forward to fill in all missing values till all missing fields have been filled in. And this can result in introducing significant bias into your dataset. And because of this tendency to introduce bias, LOCF is not often used in practice. Another imputation technique that you can use to deal with missing data is mean substitution. For each missing value in your dataset, substitute the mean of all of the other available values. The advantage of using this particular technique is the fact that it does not change the mean for that particular variable. However, every technique comes with its own disadvantage. Mean substitution has the effect of weakening correlations that exist between columns of your data. When you use mean substitution, there is no relationship between your imputed variable and other variables that exist in your data. And this can be problematic when you want to perform bivariate analysis to determine relationships that exist between variables. A third imputation technique that you can use to deal with missing values is fit a model. You can fit a regression model to predict missing columns based on other column values. The use of regression imputation has the opposite problem of mean substitution. Regression tends to strengthen correlations between your variables. The variable that you use to predict the missing value will be more strongly correlated with that missing value. Thus, every imputation technique has its own set of trade-offs. Regression and mean substitution have complementary strengths, and you might want to choose one over the other based on your problem statement. Another common problem that you might encounter when you're working with data in the real world is that of outliers. What is an outlier? A data point that differs significantly from other points in the dataset. Now, this outlier might be a genuine data point, in which case it represents information, or it could be an erroneous recording. When you're working with outlier data, there are two steps that you need to follow. The first step is to identify outliers that might exist. And the second step is to cope or deal with these outliers. So, how would you determine whether a particular data point is an outlier or not? One way is to see the distance of that data point from the mean or the average of the data set as a whole. Now, this works well if you're working with univariate data that has just one variable. Another way of identifying outliers is to plot all of your data points in some kind of coordinate plane and fit a line on that data. Points that are far away from this fitted line can be considered outliers. Once you've identified points that are outliers, there are three broad techniques that you can use to deal with this. You can either drop all points so that you ignore outliers altogether. This is what you choose to use if you feel that outliers are errors in measurement. You can replace outlier data with a certain maximum or a minimum. You can cap or floor your outlier data points. This will allow all of your points to lie within a range of your choice. And a third way to deal with outliers is to set the outlier data points to the mean or average value. Let's first talk about the two techniques that we've discussed here for identifying outliers: distance from the mean and distance from the fitted line. We'll discuss the first of these techniques to start off with, where we use the distance from the average value of the dataset to determine whether a point is an outlier. If you have data in one dimension, the mean or the average is the one number that best represents all of your data points. You simply sum up all of the values and divide by the number of data points. When you're describing data in one dimension, variation in the data is important too. Do the numbers jump around? One way to find out is to use the range, which is simply the maximum value minus the minimum value. When you use range to describe the dispersion in data, the range ignores the mean and is heavily swayed by outliers that might exist. And that's where the variance of your data set comes in. From the fitted line. We'll discuss the first of these techniques to start off with, where we use the distance numbers jump around. One way to find out is to use the range, which is simply the maximum value minus the minimum value. When you use range to describe the dispersion in data, the range ignores the mean and is heavily swayed by outliers that might exist. And that's where the variance of your data set comes in. When you use descriptive statistics on your univariate data, the variance is the second most important number to summarize the set of data points. How is variance calculated? We'll first need to calculate the mean deviation for our data. For every data point xi, if you subtract the mean of that data, that gives you the mean deviation. If you compute the square of mean deviation, what you get is the squared mean deviation. If you sum up the squared mean deviations across your entire data set and divide by the number of data points that you have, that's when you get the variance. Empirically, it has been found that our estimate of the variance for a particular data set can be improved by tweaking the denominator that you see here. Simply use n-1 instead of n. This is called Bessel's correction and gives you a better estimate of the variance. The mean and the variance of your data can be used to succinctly summarize any set of numbers. You know the formulas for each. Now, the standard deviation is another term that you might have heard. The standard deviation can be calculated from the variance using a very simple formula. The standard deviation is the square root of the variance. The mean and the variance of your data can be used to succinctly summarize any set of numbers. You know the formulas for each. Now, the standard deviation is another term that you might have heard. The standard deviation can be calculated from the variance using a very simple formula. The standard deviation is the square root of the variance of data. These two numbers, the mean and the standard deviation for any data, are often used to identify outliers. Points that lie more than 3 standard deviations away from the mean are considered to be outliers. Let's move on to our second technique to identify outliers by measuring the distance from a fitted line. For the sake of simplicity and so that we can represent this in a 2D view, let's consider data in 2 dimensions. You can see very clearly from this graph that there exists a relationship between x and y for this data. It's possible to express this relationship using some kind of mathematical formula. Outliers might be data points that do not fit into the same relationship as the rest of the data. So you might imagine that there are points on this coordinate plane that lie far away from the existing points. They do not fit into the same relationship. These points can be considered outliers. We've discussed earlier that there are 3 techniques that we might use to cope with outliers: drop, cap or floor, or set to mean. Let's consider dropping the data point or setting the data point to the mean. The first step is always to scrutinize the outliers and see why they exist. Do they represent genuine points or are they erroneous observations? If they are erroneous observations, then you'll drop if all of the attributes of that point are erroneous or wrong. If for a particular record, all of the fields are wrong observations, there's no point in having that record in there. You'll simply drop the data. Now, you might choose to replace a particular data point with the mean if only one attribute of a record is erroneous. This means that all of the other attributes of that record hold information. You don't want to lose that information. You'll set that particular field which has an outlier value to be the mean. Now, if the outlier data point is not a mistake, it's a genuine, legitimate outlier, there are several options open to you. First, you can leave as is if the model that you're trying to fit on the data is not distorted. in any way. If the outliers do not affect your analysis, you leave it as is. If outliers do affect your analysis, you can cap or floor the outlier. You'll first need to standardize the data. Standardizing the data involves subtracting the mean value of the data from all of the data points and dividing by the standard deviation. All of your data points will then be expressed in terms of Z scores or number of standard deviations away from the mean. You'll cap all positive outliers to be just 3 standard deviations away from the mean, and you'll floor negative outliers to be minus 3 standard deviations away from the mean. And with this, we come to the very end of this module where we understood and studied data cleaning and preparation techniques. We first identified the various problems that hinder analytics, such as duplicate data, missing data, and the presence of outliers. We then discussed common technology tools that we might use to work with data. If you want quick prototyping and something simple to use, you'll work with Microsoft Excel. If you want something that is production ready and works with big data, you'll choose a data warehouse and SQL or Python with Spark on a distributed system. Data in the real world will definitely contain missing fields and values. We discussed two broad techniques, deletion and imputation techniques to deal with missing data. We also discussed how we could deal with outliers and erroneous data. In the next module, we'll see how we can apply the techniques that we just discussed here. We'll see how we can prepare data for analysis using Microsoft Excel and Python. Hi, and welcome to this module on preparing data for analysis using spreadsheets and Python. In the previous module, we studied the different ways in which bad data can hinder analytics. Missing data, duplicates, outlier data, all of these are problems that we need to deal with. In this module, we'll use two different technologies, Microsoft Excel spreadsheets as well as Python on Azure notebooks to deal with these problems. We'll first start off working with Microsoft Excel and see how we can use this tool to deal with missing data. We'll specifically look at two techniques, list-wise deletion and mean substitution. We'll then move on to identifying outlier data using Microsoft Excel. We'll plot a box plot representation of our data to visualize outliers. And once we've identified them, we'll see how we can use ZScores to deal with outliers in Excel. We'll then move on to a different tool and technology to work with data. We'll use Python on Microsoft Azure notebooks to deal with missing data as well as outlier data. In this demo, we'll see how we can apply some data pre-processing and preparation techniques using Excel spreadsheets. Here we are on a brand new Excel workbook. The workbook is named Mobile Price, and the sheet that we are working on is called Duplicates and Missing Values. Here we have some data about mobile phones already loaded into the sheet. This data comes from data that's freely available on kaggle.com at this URL that you see here. This is a dataset that can be used for machine learning, and it contains a number of different features of different mobile phones. These are features like battery time, whether it has Bluetooth or not, clock speed, whether it has a dual SIM or not, and a number of other details. A simple step in data preparation is to rename columns so that their names are meaningful. Here I'm going to rename the blue column, which represents Bluetooth, to be Bluetooth. And I'm going to rename a number of other columns as well. The megapixels of the front camera is FC underscore megapixel. The depth of the mobile is M underscore depth. I'm going to rename the column representing the megapixels of the primary camera to be PC underscore megapixel. Data sets in the real world have to be cleaned before they can be used for analysis. Let's say your data contains duplicates and you want to get rid of these. You can head over to the data menu option on your Excel workbook, and on the ribbon, you'll find an option which says remove duplicates. Now, this brings up a dialog which allows you to select in which columns you want to look for these duplicates. All of the columns are selected by default here. I accept these settings and click OK. Excel very helpfully lets me know that there were two rows that were duplicates, and Excel got rid of these. That's exactly what I wanted. I hit OK to continue working with my data. Now, I'm going to specifically work with the RAM feature in my data set. Select the Home menu option, and here in the ribbon, you'll find an option to sort and filter based on the RAM. Choose the filter option, and this will allow you to filter values. Notice that there is a little icon that shows up, and selecting this icon will bring up the filter dialog for this particular column. By default, all values in this column have been selected. I'm going to deselect select all in order to select specific values. If you scroll down, you'll find an option to select just values which are blank for this column. If you click anywhere outside, this dialog will disappear, and this will allow you to see which records contain missing values for RAM. When you're using this data for analysis, you may not want missing values in any records. And there are different techniques that you can use to deal with missing values. Here I'm going to select both of these records, right click and choose the delete row option to get rid of these records altogether. Once I've deleted these records, I can click on the filter icon once again and clear the filter that I've applied on the RAM column. Click on clear filter and get rid of this filter. This data set has missing values in other columns as well. I'm going to select the m_depth column, select all of the values within this column, and under the home menu, go to the find and select option on the ribbon. This brings up a little menu which allows me to go to special, and this brings up a dialog that allows me to select cells in this column based on the constraints that I specify. I want all of the blank cells in this column to be selected. Blank cells mean that data is missing for this column, and I want to be able to deal with this missing data. Here is a blank cell that is highlighted. Other blank cells in this column will also be highlighted. Another way to deal with missing values in a column is to fill in those values with something meaningful. Let's say you want to fill in zeros for all missing values, and that's exactly what I do here. You can fill this in into one of the cells and hit Control Enter, and all of the blank cells will now have zeros filled in for m_depth. We'll see another technique to deal with missing data here. For that, we need to perform some calculations. We'll select the top row of this particular sheet, right click and hit insert so that we get an additional row above the first row. The mobile weight column also has missing values, and I want to fill in these missing values with the average of the mobile weight. I'm going to calculate the average using an Excel formula. Excel formulas are preceded by an equal to sign, and average is the name of the Excel function. Once you open up brackets, you can select a particular cell where you want the average calculation to begin, and then hit Shift and the down arrow key to select all of the cells in this column. Observe the formula bar in Excel. You can see that the average will be calculated for all values from J3 all the way to J2000. Hit enter to calculate this formula, and 141.27 is the average weight of a mobile. We'll now fill in the missing values in the mobile weight column with the average weight of a mobile. Select the column, go to find and select, and choose the go to special option. This will allow us to select all of the blank cells in this particular column. When you hit OK, you can see that all of the missing values are selected in one go. Now let's fill in a value that we'll use to replace these missing values. That is 141, the average weight of a mobile. Hit Control Enter, and you'll see now that all values that were previously missing now have the value 141. When you work with data in the real world, it might contain outliers, which might be mistakes that you made while recording the data, or genuine data. In any case, there are several different techniques that you can apply to work with outliers. and we'll see how you can apply some of these techniques in Excel. Now we're working with the same data set as before, but on a brand new Excel workbook and a new sheet, and we're using only 3 columns of the original data: the mobile ID, mobile weight, and RAM. Let's visualize the data in the mobile weight column. Select the column, go to Insert, and in the ribbon, you'll find the option to visualize this data in the form of a chart. If you click on this chart drop-down, you'll find an option to create a box and whisker plot. A box plot is a standard visualization technique to see how your data is spread out. The box isn't really very clearly visible in this small view, but these little points that you see at the very top represent outliers. These are mobile phones in our dataset that are clearly very heavy, outliers in their weight. I'm going to make this chart just a little bit bigger so that it's easier to see. The box represents all of the data that are within 25th and 75th percentiles in our dataset. The little vertical lines are whiskers, and the horizontal lines that connect to these vertical lines drop down. You'll find an option to create a box and whisker plot. A box plot is a standard visualization technique to see how your data is spread out. The box isn't really very clearly visible in this small view, but these little points that you see at the very top represent outliers. These are mobile phones in our dataset that are clearly very heavy, outliers in their weight. I'm going to make this chart just a little bit bigger so that it's easier to see. The box represents all of the data that are within 25th and 75th percentiles in our dataset. The little vertical lines are whiskers, and the horizontal lines that connect to these vertical lines are caps. They represent 1.5 times the interquartile range. Data that does not lie within this range are considered outliers, and you can see that there are 3 outliers here in this mobile weight box plot. We'll now visualize the RAM data in our dataset using the same box plot as before. Select the column, go to Insert, select the chart drop-down, and choose the box and whisker plot. If you visualize all of the RAM details of the mobiles in our dataset, you can see that there's exactly one outlier. This is the RAM box plot. I'm going to resize this box plot as well using the knobs provided, and once I've done so, I'm going to move it and place it right next to the mobile weight box plot. Here are the 2 columns in our data which contain outliers. I'm now going to calculate Z-scores for the mobile weight column. Z-scores are calculated by subtracting the mean from all of the column values for the mobile weight and dividing by the standard deviation. Z-scores will allow us to express every value in our column in terms of multiples of the standard deviation, and this makes it easier to identify outliers. Anything greater than 3 standard deviations from the mean can be considered an outlier. In order to represent the mobile weight and the RAM values using their Z-scores, we need to calculate their mean and standard deviations, which I'll do. Off to the side here. The average or the mean of the mobile weight can be calculated using the average Excel formula. Select all of the values in the mobile weight column to specify as an input to the average Excel function. We've seen earlier that the average weight of a mobile is about 141 grams. The standard deviation of values in a particular column can be obtained using the stdev function, equal to stdev, and select the mobile weight column once again. This will give us the standard deviation, which is equal to roughly 45 for the mobile. weight. Now that we've calculated the mean and standard deviation for the mobile weight column, we can do exactly the same thing for the RAM as well, 21. And here you in order by the standard deviation, you simply use the standardize Excel function. The first input to the standardize function is the column of values that you want to standardize. This is the mobile weight column, so select it. So that is the B column. The second input is the mean of this column, which is present in cell K7. And the third is the standard deviation, which is present in cell K8. Here is the Excel formula that we use to standardize this data, that is converted to Z-scores. Standardize range, mean, and standard deviation. You can see that the Z-score for a mobile weight of 188 is 1.03. It's roughly one standard deviation away from the mean. I'm going to drag this formula down to fill in the other column values, but before that, I need to ensure that our references to the cells that hold the mean and standard deviation for this particular column do not change when I drag the formula down, which is why I specified $K, $7, $K, $8. You might already know that the use of the dollar sign in Excel will lock that cell when we drag down the column values. So now let's use that little knob at the corner and drag down this particular cell formula to fill up all of the cells in this column. Another option is to simply double click on that cell and it will fill in all of the column values. We now have Z scores for the mobile weight. I'll now create a new column of the Z-scores of the mobile weight, but this time with the outliers removed. Anything which is greater than 3 standard deviations from the mean, I'm going to consider an outlier. So my outlier range is -3 to 3. Any data point that lies 3 standard deviations on either side of the mean, we consider an outlier. In order to identify and remove outliers, we'll use the if function in Excel. If the z-score is 3 standard deviations away from the mean, we'll replace it with a blank. Notice that we have an OR function nested within the if function. The OR function basically checks whether a particular z-score is within the outlier range or not. We've specified our outlier range using the z-score in the cells K10 and L10. If a particular z-score is within 3 standard deviations of the mean, we use that z-score value directly. That is the z-score in the cell D2. If it's beyond 3 standard deviations away from the mean, we simply replace it with a blank. Once we've specified this formula, you can double click on that little knob in order to fill in this formula for the entire column. If you want to view the outlier values that have now been replaced using blanks, go to Sort and Filter, and in this menu, choose the Filter option. This brings up the little filter knob on the column header, and use this filter knob, bring up the dialog and filter by blanks. And you can see that there are 3 values that were outliers and have been replaced using blanks. These were the very heavy mobiles that we had visualized in our box plot. Bring up the little filter dialog once again and hit select all so that all values are once again displayed in your sheet. In this demo, we'll use a slightly different technique to deal with outliers. Let's calculate our z-scores for the RAM data first. We've already calculated the mean and standard deviation of the RAM values, which means we can use the standardize function in Excel directly. We want to standardize the RAM values, so go ahead and select the RAM column and then specify the mean and standard deviation as the input to the standardize function. Remember that these scores are calculated by subtracting the mean from every value in the dataset and dividing by the standard deviation. We want to use this formula in every cell in the RAM z-score column. We want to make sure that our references to the mean and standard deviation remain unchanged as we copy this formula, which is why we use the $sign to lock the mean and standard deviation cells. In order to calculate the z-score for the entire column, select that little knob and double click, and Excel will automatically fill in the formula for the entire column. I'm going to add in another column here named RAM z-score clip. I want to clamp all values that are outliers to be 3 standard deviations away from the mean in either direction. And one way to do this in Excel is to use two if functions, one nested within another. This nested if function operates on the z-score that we've calculated for RAM values. It'll first check to see whether a particular z-score is 3 standard deviations away from the mean in one direction. If the z-score value is less than -3, it'll simply clamp it to -3. If the z-score value is greater than +3, it'll be clamped to +3. And if the z-score value is within the outlier range, that is 3 standard deviations away from the mean, we use the value as is. Once we've set up the formula for one cell, we simply double click that little knob at the bottom right of the cell to fill in this formula for all of the cells in this column. Select this column and go to Sort and Filter to filter and view this data. In the menu, select the Filter option. This will set up that little knob that will allow us to filter this data. Clicking on this knob will bring up the filter dialog and select all values which are exactly equal to 3. You can see that there are 2 mobile phones in our dataset which are outliers in their RAM values. They have very high RAM and they have been clamped to 3 standard deviations. If you want to view all of the rows once again, bring up the filter dialog and choose Select All. We saw how we could deal with outliers in 2 different ways, but how do you know that these outliers have been removed? Let's select a particular column. Here is the mobile weight z-score removed. Go to Insert and let's select the box and whisker plot once again. When you apply this box and whisker plot to the z-scores, you can see that there are no outliers. For the mobile weight column, we had replaced all of the outlier data with blanks. Now let's visualize the RAM z-score clipped column as well using a box plot. Select the column, go to Insert, go to the charts and choose the box and whisker plot. Once again, this visualization makes it very clear that all of the outlier data are 3 standard deviations away from the mean. In this demo, we'll see how we can clean and prepare our data for analysis using Python. We'll write a Python code on hosted Jupyter notebooks. These are Azure notebooks on the Azure cloud platform. In order to work with notebooks on the Azure platform, you need to have an Azure subscription, which you can create for free. Azure notebooks can be accessed at notebooks.azure.com. If you don't already have an Azure subscription, you can use this page to create one. Or you can go ahead and sign in with your Azure account. account using the sign in button on the top right. This will bring up a page where you can specify the username and password for you to sign in. Now I have a personal Azure account, and that's the choice I make here. It's not through an organization, and I specify the password and sign in. All of your Azure notebooks are grouped in logical units called projects. Click on the My Projects link here on top in order to view all of the projects that you have set up. I have one other project here, but I'm going to create a new project to work on the notebooks that I'll use in this course. I call this project Preparing Data. Notice that Azure automatically assigns an ID for this project. This ID will be used as a URL prefix for all of the notebooks in your project. You can choose to make these projects public if you want to, if you want others to have a look, but I'll leave that option unchecked. With our project created, let's use this drop down here to create a new Azure notebook. A notebook is simply a browser based shell where you can write code and view results right there on your screen. It's an interactive environment. Which you can use to write Python code. You can also use it for other languages, but we'll be working with Python. I'll create a new notebook called Filling Missing Values, and I'll use the Python 3.6 kernel. Once you've created the notebook, it will be listed within your project, and you can simply double click on this and it'll open up in a new tab. Here you have it, a Jupyter notebook hosted on the Azure cloud. Your Azure notebook also comes with all of the common libraries that you might use to process your data, such as NumPy and Pandas. For most of the common libraries, you don't need to pip install these packages before you use them. In order to understand and implement the different techniques that you can use to fill in missing values using Python, I'm going to set up this toy data frame in Pandas. This toy data frame has just a single column named numbers, and it has some numeric values and some values that are nans or not a numbers. These are our missing values. Your pandas data frame makes it very easy for you to check whether any column has missing values. The isNull function on the data frame will check for null or missing values and that sum function will tell you how many records are missing. You can see that our numbers column has 3 missing values. If you want to just get rid of all rows which have field values missing, you can simply call dropna. The drop NA function on your data frame will simply get rid of rows with missing values. And if you take a look at the resulting data frame, you'll find that 3 records from our original data set have been dropped. These are the records with missing values in their fields. This is exactly equivalent to deleting the corresponding rows in Excel that we saw earlier. Now, instead of getting rid of the rows altogether, let's say you want to fill in missing values with a particular default value, such as 0. The fill NA function on your pandas data frame will fill in all missing fields with the value that you specified. Here it happens to be 0. You can also choose to fill in missing values using other data points that are available in that column. One way to do this is to use the bfill or the backfill technique. You can see in the result that all of the missing values have been filled in with the value 7. So 7 was the next value after all of the missing values, and 7 was used to backfill the missing field. In exactly the same way, there is a forward fill or an F fill technique available in pandas as well. Here, if you take a look at the result, the value 3, which is the value immediately before the missing value start, has been used to forward fill the missing values. In the forward fill, the value just before the missing value will be considered, and that value will be used to fill in the missing data. Another technique to fill in missing values that we encountered in Excel is to fill in missing values with the average of a particular column. Simply call fillna and calculate the average by invoking the mean function on your column. And here in the result, you can see that the missing values have now been filled in by the average value of this column. Data frames also allow you to use statistical interpolation techniques to fill in missing values. Simply call interpolate and it will estimate the values that should go in the missing fields. Interpolation is a mathematical technique where you construct new data points within the range of a discrete set of known data points. And that's what Pandas has used here to fill in missing values. In this demo, we'll perform some data cleaning operations using Python on an Azure notebook on a real-world dataset. I'm going to upload this data using this upload option available on my Azure